So anyhow, so we finished the power consumption last time, and now this lecture we're going to be talking about interconnections or wire, basically the metal connections, metal and semiconductor connections between the gates. So let's see. So in the schematic, this kind of shows this thing. We draw lines that connect gates together, but physically, basically there are sort of layers, metal layers, I think that we talked about. My pen isn't working too well. So that, basically you route these layers between your gates physically. And these layers have, they have resistance, they have capacitance, they have inductance, which for the most part you don't have to worry about unless you're going very, very fast. They have crosstalk. They have reliability issues potentially. So a lot of things that you need to consider. And it's a big part of the design. I think we've been focused mostly on the gates so far, but given the resistance and capacitance of these wires, they tend to be just as important as the gates themselves in calculating delay and power consumption. And, it's the truth is that most of the chip is like, I think there's a nice picture here. This is a scanning electron microscope cross section of two chips, one in a 90 nanometer process, the other one in a 45 nanometer process. But the thing that's the same for both of them are transistors, are these little guys at the bottom. I think here's another transistor, maybe another transistor here. It's a little hard to tell. But they're really, if you look at a chip, most of it looks like interconnections. Okay, so, the transistors do all the switching and all that kind of stuff, but the interconnections are the majority of the area and also the volume of the active part of the chip. And so let's see, what else do I want to say? So they affect, everything that we talked about: speed, power consumption, and noise. So the way, this is, again, two processes, 90 nanometer and 45 nanometer stack. So let's take a look at the differences between them. One of them is older processes had fewer metal layers. So, I haven't seen an end to the number of layers, but, it might be 10, 11 layers now. But you can see a 45 nanometer process is up to 8 layers. The 90 nanometer process was 6 layers. What else do I want to say about this? The other interesting thing is that as you go higher up in the stack, so this is the transistors, this is the silicon surface. As you go away from the silicon surface, the metal thicknesses get thicker and thicker. So a metal 7, you can see, I don't know, it looks like it might be 5 or 6 times thicker than a metal 1. And also the pitch of the metals gets bigger and bigger. So here you can see the separation between these two metal 8 layers. Whereas, when you're down here, the metal 1s you can put pretty tightly together. So, so we get thicker and bigger pitch. And, so the reason for it is, basically you end up using these top layers mostly for power and ground connections on your chip. And you need a lot of that, and you need it to be low resistance. So need low resistance. And the reality is, as they process these wafers, it gets more and more difficult for them to get these layers flat as you go up higher and higher. So they're trying to give themselves a break from a how tight the geometries can be as you go up, sort of loosening up the geometries as you go up. Another interesting thing to note is, at least when I was started doing chip design or studying it, I always thought that interconnections for whatever reason were like rectangles, but they're really more like rectangles like this kind of now. They're the aspect ratio, as you can tell here, like the aspect ratio between height and width, they tend to be usually, as much as 2x higher than they are wide. So that has implications for capacitance, etc. So, but just something to keep in mind. Okay, so in terms of modeling wires, you have, and imagine if you have these wires running next to each other. Okay, so imagine each one of these is one of those wires, and they're running next to each other. Well, the wires themselves have capacitance to ground. They have capacitance to each other, because they're, if you imagine if these are these high aspect ratio wires running, how should I draw this so it doesn't look too confusing? Just from the fringe capacitance between those lines, you get the capacitance. You will have resistance of the wire, as you go from one side to the other. These are metal wires. They're usually aluminum or copper. And as we see, you have to consider that resistance. And that combination of resistance and capacitance gives you RC delay for the wires. The capacitance between the lines gives you crosstalk. And inductance exists on chip, but for the most part, you can ignore it, except when you have things that are going very fast for very long distances. Basically, like, on purpose, if you're building a transmission line, you can ignore inductances on chip. Off chip, you usually cannot, on your printed circuit boards, etc. You cannot ignore inductances, just because the inductance values are higher, the distances are longer, and so even for the same speeds, you have to be worried about inductance. But on chip, it's really more of an R resistance and capacitance type of consideration. Okay, so let's see. We talked about this already. We're not going to talk about the parasitics. I mean, we're going to talk about this amount of parasitics in terms of delay. Well, so before I say anything else, interconnect parasitics are these R's, C's, and L's. Ideally, an interconnect would have zero resistance, zero capacitance, etc. So any of these factors that make for real interconnect, they call parasitics, but it's really inherent to a metal wire. So that if we look at delay, power consumption, those kind of things. I don't think we're not going to talk too much about reliability, but reliability is also an issue because of various things that happen in the wire, like over long periods of time, over temperature. You have to worry about a few things, but we're not going to talk about them very much, but something to worry about. They tend to be less reliable than transistors. So this plot is supposed to give you guys an idea about, how wires, how they're distributed in terms of length. So horizontal axis is length, vertical axis is the number of nets. So it's a histogram essentially. So when you're looking at And this is many generations of, they're older processors, but I think this still holds, these old Intel processors. But what happens is there are and remember this is a log scale on the vertical axis here, there are very few nets that are very long. Most of the lines, most of the nets are local interconnects. They're very, very short. You can see they're like, 100 microns or less. And there's very, very few that are that run the whole length of the chip. They tend to be clocks, those kind of things. Okay, so just jumping into the capacitance first. Are we going to talk about capacitance? No, let's. I think. Let's see what I want to say about this. Let's jump through this one. Okay, so here's sort of some definitions about the wire. You've got, if you think about two wires running parallel to each other, you've got the separation between them, the width of each wire, the length, the thickness, and the height over ground. So these are all, the characteristics. We talked about the pitch before, but it's basically how fast the period in space where you can repeat a wire. So it's the width plus the distance, and then you can put another in that same pitch, in that same width plus same separation. You can, put another wire here. So that's really the important thing, because usually especially when you're routing things locally, interconnections locally, you're trying to go at minimum pitch or close to minimum pitch. And again, the other thing that I wanted to say here is the aspect ratio of these lines they tend to really, in reality, look kind of like this. They tend to be tall and narrower or whatever. That's sort of this aspect ratio of 2 is what you would normally expect. And we'll see how that affects capacitance. So this is some typical things we talked about already. Older processes had fewer metal layers. New processes have more metal layers. Metal one tends to be thin, narrow, and high pitch density. And the top layers tend to be for power ground, global nets. And so that's the typical stack. And the number of layers, I think I already mentioned this, is going up in the more advanced processes. Okay, I don't know if this is useful for you guys, but this is sort of how they're modeling the interconnections. Resistance is how narrow your pipe is. Capacitance is, this throw that needs to get filled. And then this inductance is this wheel that opposes the flow of the water. Since we don't worry about the wheel, I guess the analogy here, or maybe I guess you can think about the wheel too, but the analogy here is all things that are resisting, because there's actually an aspect called resistance. I guess these are fighting against the flow of current or flow of signal, or whatever you want to think about it, from one end of your connection to the other. Either, it's just the narrowness of the pipe is making it hard to get current in there, or, before you get a signal in, you actually have to fill out something else, or something's actually working against you. So they're all sort of fighting against you. So a lot of times when we're, unless you guys have taken like radio frequency or microwave design, or I'm sure most of you have taken electromagnetic design, but so when you think about a wire connecting from one end, So, I put a voltage source here that's changing. Boy, that didn't do a good job of that. And then you have some kind of a termination here. So what you start with is you have electromagnetic waves that are basically affecting the flow of electrons and holes. And you can actually think of these as standing waves, etc. So you would start with something like Maxwell's equations here. And then, that's in E&M. It's the same piece of metal in E&M. And then you go to, you go to a transmission line model that has a RLC when you do sort of microwave design. And then typically in a circuit class, probably so far, you've been kind of thinking of it as sort of a lumped model, having an R and a C, okay? But in reality, in chip design, you're somewhere in between these. This lumped model of just thinking of a line. Of course, this depends on how long the line is and the values for the R's and C's. But typically, this RC for medium length to long length lines is not, it's not good enough. And something like, if you try to do a transmission line analysis on every line, that's also like a little too much because you're not going fast enough to worry about it. So I think the appropriate thing is this distributed. You basically break up your RC line into small lengths of RC. So from a modeling point of view. Okay, so instead of this, you have basically R over, each segment is R over N, resistance, capacitance is C over N, R over N, C over N, and then you have N segments, say. Okay, and the finer the detail you want, the more these segments you put in. Okay, so putting in a lot of segments, it's difficult to deal with. Imagine let's say if you want to use this for a hand calculation and you want to do an Elmore model for, a whole lot of segments, that would take you a lot of calculation, right? If you guys remember the Elmore models where we had, whatever, I'm not going to draw it, but from our the delay lectures. So what you do is, there's a couple of amazingly efficient models called the pi model and the T model that are very, very close to something like this. So for example, it says a 3-segment pi model is accurate to 3% in simulation of a long line. And this is what the pi model looks like. So let's say if you had a R and a C, the pi, the reason I call it pi, I guess it looks like the numeric or whatever pi symbol. Okay, you put half the capacitance to ground and half the capacitance to another. Okay, so that's the pi model. The T model, I guess, works also, but I think the pi model is a lot more popular. So let's see what this says. So let's say you had a capacitance of, well, let's say you had a resistance of 300 ohms. Well, that's a lot of resistance. Let's say 30 ohms. You know what? Yeah, it's probably more like 3 ohms. And a capacitance of, well, was it? I'm trying to think of something that adds up. let's call it 30 ohms, doesn't matter. And 600 femtofarad capacitance. So I want to do a 3-segment pi model of this. Okay, so what you do is you divide this by 3. Okay, so you put in 100 femto, 10 ohm, 100 femto, and you repeat that 3 times. Just copy it. This thing out of the way here. So what you do then is you connect these guys up. Okay, so in total here, so this ends up being, so this is in, out, in, out. Okay, so in total we have 100, 300, 500, 600 femtofarads of capacitance, okay, in 3 pi models that are connected together, and then 30 ohms of resistance. And so, this model is, like it says, very, very close to simulation. So it's amazingly accurate. And, we'll be using this for our models. Yeah, I'm not sure where the math comes from and why this thing is so accurate, but it is. So instead of using a very big number of resistive capacitor network or using just a lumped RC line, this pi model with 3 segments is very, very good. Okay, so that's a distribution of a model. Let's look at the resistance now. So one of the things that confuses everybody, all the students, every semester, is this concept of sheet resistance. Okay, which is when you do designs, it's extremely useful and efficient, but I guess it's conceptually kind of confusing. So if you just were worrying about the resistance of a line, right? Let's say take this wire here, right? So the resistance would be, the longer the wire is, the more the resistance, right? The wider it is, the less the resistance. The thicker it is, the less the resistance. And then, so this is the geometrical thing, is L length over width times thickness. Okay, it tells you is sort of proportional to resistance. And then you have to throw in the resistivity also. So it depends on, so rho is kind of like resistivity, depends on material dependent. So if you had aluminum, it would have one resistivity. We'll look at that in a little bit. If you had copper, you'd have a different rho. So like copper has lower resistivity than aluminum, but that's basically the resistance of that line. Now, when you're doing chip design, you don't control the thickness. The thickness is whatever the thickness of that line is given to you by the process engineer. So it's inefficient to keep using this thickness in your calculations of resistance. When you draw a line in your layout tool, basically there's no reason to keep calculating the thickness, because the thickness is always the same. So what people do is they basically wrap up this resistivity over the thickness into a single thing called a sheet resistance. And its units is ohm per square. Okay, so stay with me now. Okay, so why ohm per square? Because if you then look at just the L and the W, if you just look at the L and the W, so I look at the L and the W from the top. So let's say I have a metal line that is I don't know, 300 microns thick. Oh, sorry, 3 microns long. So I'm looking at this from the top. Okay, and it is 100 microns wide. Okay, I can put in 3 squares here, 3 unit of things that have the same length and width. And I can just multiply this 3 square. So something, a line that's 300 microns long by 100 micron wide is 3 square. And I'll just multiply that by the resistivity in terms of squares. So that's given in terms of ohm per square. And basically these squares cancel each other out and I end up with units of resistance. Now, if I had a line that was 30 microns long and 10 microns wide, I would still only get 3 squares in there. So it would have, these two would have exactly the same resistance, which makes sense because the length and width, the ratio with each other, the ratio is the same. So end up with the same resistance. So it's a lot easier when you're drawing these connections in your layout and you're looking at them from the top to just take the length divided by the width and multiply it by the sheet resistance than it is and that sheet resistance will be a different sheet resistance depending on which layer you're talking about, whether it's metal 1 to metal 9 or whatever. So it's a lot easier to do that instead of keeping track of each layer, what the thickness is, and add to the thickness, etc. So it confuses everybody, but basically you're creating this thing, this parameter called sheet resistance, which is the resistance, it's the resistivity of a line of a certain thickness of a certain material. And then you can just multiply that by length over width to get the resistance. Any questions about that? We'll do a quick example a little bit down the line here, but that always
would help.
Okay. So let's see. Okay, so before we get into the example, I got a couple other things to say about the materials that are used for these interconnections. And aluminum used to be the most popular. Okay, so these are just some random layers, but really the ones you see in chip design are copper, aluminum. You see this tungsten, you see it for vias or the connections between the wires. Gold you see in like wire bonds. Silver, maybe you see it sort of silver paste connection. Let's just forget about silver. You see it. I don't want to confuse you guys. But the main ones we're concerned about in terms of routing on chip are copper and aluminum. And aluminum used to be the popular choice until, like it says, until 800 for bigger processes. Oops, older. What happened in sort of maybe around early 2000s is, this resistance of aluminum started being a bigger and bigger problem. So people were looking for something with lower resistivity that was inexpensive, et cetera. And, they chose copper that was reasonably easy to deal with and had a much lower resistivity than aluminum. And so those are the two you see. Now, one problem with copper is the resistance is low. So copper, you'll see it like very often in newer processes, but it has a couple of problems. One of them is that it's corrosive to transistors, and the second thing is it oxidizes. So when you're trying to connect to the chip, it makes things difficult. But let's talk about the. But by the way, one more thing I wanted to say about this is that in practice, so this is the bulk, so-called bulk resistivity. Okay, if this was, if you had a centimeter by centimeter chunk of copper or aluminum or something. When you have these wires on chip, the wires are thin. You're talking about a fraction of a micron typically, and so you have things like scattering on the surfaces. You have, they're not a solid chunk of metal. They can have grain boundaries, so the actual resistances tend to be higher. So if you look at resistance on chip, so resistivity of copper is around 2.2 to 2.6 microohms centimeter, and aluminum, so it's a little bit higher, and aluminum is 3.6, sort of roughly, depending on how they make it. So just remember, it tends to be a little bit higher. Okay, so that's for the choice of materials, and I guess I should jump to here about the issues with copper. So copper can diffuse into silicon and cause a problem. So what they actually do, there's actually a very complicated process for depositing copper, and they have to put in a barrier around the copper to prevent the copper from basically leaching out to connect to transistors. Then you put, say, vias here. So the transistors don't see the copper. This might be a tungsten or something like that. But you have to put this barrier, which makes this copper, the width, less than the drawn width, because you have this barrier. Okay, plus there's issues. This is comes with how you deposit the copper and how you flatten it, something called dishing. But all of these, what they do is they reduce the actual usable cross section of your copper line. So the effective resistance of copper isn't, it doesn't give you as much of an advantage as you'd hoped for over aluminum, but it's still an advantage. So it's something that's used, again, in all the advanced processes or copper processes. And then before we go to the example, another thing that's extremely important is you could spend all your time, getting a very low resistance line made, but then, if you put in too few vias or contacts between metal lines, you can increase the resistance significantly, because the vias and contacts have a huge resistance each, 2 to 20 ohms. Now notice we're talking about microohm centimeters. We'll see basically the resistance of even the thin lines is pretty low. If you have 100 micron long piece of metal, it might not give you as much resistance as a single via or contact. And so you have to be really careful with that. And basically the way you deal with it is by putting in as much vias, contacts, etc., as you can in parallel to reduce the resistance. Sometimes you can't, you don't have the space to do it, but when you can, you really have to do it. If you have, two lines, two narrow lines, let's say you got metal 1 and I don't know, metal 2, you can drop in a contact. Say you can drop in a contact and you extend the metal 2 over the contact, and you extend the metal 1 over contact. So if you have the space, the thing to do though is to drop in multiple contacts and extend your metal 1 to cover. And again, you can take this as far as you like, but sort of get as much overlap here. And now here you've got 3 vias in parallel. So, you have a third the resistance, and it can be pretty significant. It can dominate. And also, I think I might have mentioned this before, but vias, contacts, these things, they are the lowest reliability thing in your chip design. So it's not like there's a good chance that they'll go bad, but they have the highest chance of going bad, and there's so many of them on the chip. You always, whenever you can, you want to at least double up on and more on vias, contacts from a resistance and a reliability point of view. Very important to do that. Okay, so let's do an example. Let's see. And you guys can peek because it's the next slide. But let's say you had first it wants just to figure out the sheet resistance. So this is R squared. Okay, rho over T for a copper wire. That's 0.22 micron thick and has a resistivity of 2.2 times 10 to the minus 8 ohm meter. Okay, so the first thing we want to do is this sheet resistance. Okay, and then you want to find the resistance of a wire with length 1 millimeter and width 0.125 millimeter. So this is A, this is B. Why don't you guys give that a shot and we'll see if we can figure it out together. Okay, any volunteers? Nirupam, you want to step up?
Well, I'm not entirely sure, but I think it's the resistance per meter we found, and that times the length over the width.
Yeah. So let's do it though. Let's get the numbers. So how do you get the resistance parameter?
So 0.10 multiplied by 1 millimeter over, or 1 meter.
So
One
here, yeah,
meter.
you're a step ahead of me. So here you want to do 2.2 times 10 to the minus 8 ohm centimeter, which is the resistivity divided by the thickness.
Mm.
And this gives you 0.10 ohm per square. And here, like I said, the resistivity is this guy, the resistance, total resistance is 0.10 ohm per squared
Yeah.
times, go ahead.
Then it would be 1 meter over
Sorry, it
point
should be 1 millimeter.
125 meter.
Yeah, that's the same. I guess it'd be the same ratio. I forgot to write the meter and millimeter for both, so it would have been their same resistance.
Oh, okay.
Um, so, and then what would this be? 1 millimeter over, so this into this is 8 into, wait. So if it's 1 millimeter, it's 8.
Yeah, that's like 8.
So this ratio is 8.
Yeah.
And we multiply it, so we get 0.8
Yeah.
ohm. The squares go away. Okay, or so how come? This is interesting. The solution thinks it's a millimeter over 0.125 micron, which doesn't make any sense. But anyway, so you end up with these numbers, you end up with 0.8 ohms. Okay, so notice once we calculate this once, let's say this will happen to be your metal one for the sake of discussion, resistivity. So in a given process, you only calculate this once. And then whenever you have a line of a certain geometry, you just multiply it by the length over width of that line to get the resistance value. All right. So what else do we want to say? So that's how you calculate the resistance, and then basically the ways to get around resistance ends up being a really big issue when you put the chip together. And so you always want as many interconnect layers as possible. You're always fighting for that. The problem for that with that is it increases the cost of the wafers. And NRE for making the wafers. But you always want to get as much interconnect as you can to get stuff as close as you can get together to reduce the resistance. And the foundries are always trying to use better materials to reduce the interconnect resistance. But you really don't have much control over that. You kind of have what the foundry gives you. But if you're trying to select a foundry, a process that has copper interconnects, for example, is going to have lower resistance than aluminum process. So you kind of know that. Another thing about foundries, so you can reduce the resistance of gates. So it's not so bad when you have small gates, but if you have long gates, polysilicon resistance can be pretty high on the gates. So they have these things called silicide that reduces the resistance of poly, and then you can also use the poly I wouldn't use it for very long routing wires, but you can use it for very short routing, say when you're connecting the N and the P transistors of a gate. Okay, and the other thing, these are the sheet resistances or some of the different things. So, we talked about aluminum is the material. And then notice how, you can use, it's not advised, but you can use these other layers that you have access to for connections also. And it's, I guess what this says is, for example, you do not want to use diffusion to connect things together just because you have a huge resistance, and then you also end up with a huge capacitance. As you run out of interconnect layers, and you get increasingly, like if you get into some tight areas, you run out of interconnect layers, you'll be surprised. People start like getting desperate and using these layers for connections, and it like invariably bites you in the rear. So maybe short, very short distances says if you have poly with silicide, but I wouldn't, I really wouldn't use anything else. Actually, even poly, I remember my first job out of grad school was at JPL. And when I came in, they were just trying to debug a chip that wasn't working. And it ended up that they had routed I think was it a reset line or something in poly across the chip, thinking that it wouldn't matter, and it just total fail. So again, just be careful with resistances when you route, especially long distances. I would really only use these two layers. Is if you have doped poly, okay, use it for very short distances. Otherwise, aluminum or copper. And even here, you can see the huge jump in resistance between these two. So you're kind of taking a chance if you go very far. Okay, so that was all on resistance. Now the other parasitic problem that's typical is the capacitance. And at least for my, how I was introduced to capacitance is this concept of parallel plate capacitance, where you had a metal plate over over an infinite ground. So this is your plate over your ground, and basically the capacitance ended up being the width times the length times the dielectric constant of the material over the thickness. Okay, so this is common model you see for old interconnects. This also kind of applied to, but not anymore, because notice this is missing a couple of things. This model is missing the next guy sitting next to it. So you have capacitance between the lines. And the other thing it's missing is the fact that in our processes now, these tend to have potentially tend to kind of look like this, very long. So the plates, the part of the plates sort of facing each other is thick. And also that this plate has fringe capacitance to the ground. So these end up being probably more important than the parallel plate, or just as important. So first, looking at the fringe capacitance. So when you have this piece of metal, which in reality has both a parallel plate component and a fringe component, what people do to simplify the analysis is they do a linear superposition, assuming that you have a completely parallel plate with no fringing, and then just a cylindrical or circular, I guess the cross-section is circular thing that has all fringing. And the total capacitance of the wire ends up being the capacitance of both. Okay. So you guys don't need to like really memorize these equations. but you'll get, I mean, these are just various types of hand calculations. What you'll get for every process is you will get something like this. You'll get a wiring table. So for a given process, this is a quarter, and this is what you'll be working with. And so this, what this table has is it's missing this stuff, so I'll write it for you guys. So everything in the dark is fringe capacitance, and stuff in the light or parallel plate and you notice you have the same things here as here. So the way to read this is this 88, oops, this 88 is the parallel plate capacitance between poly and field. Field is the same as the substrate. Okay, and this guy here is the fringe capacitance between poly and field. Now the parallel plate capacitance is given in terms of units of, typically, it's given in units of attofarads per micron squared. But the upshot is it's given in terms of capacitance per unit area, so per area squared. So atto, just incidentally, atto is 1 times 10 to the, let's see, minus, I think 10 to the minus 18. So it's that attofarad is that many farads. Okay, so it's given in terms of attofarads per micron squared, and the fringe field is given in terms of attofarads per micron. So, assuming, the reason for that is if you had a really narrow line, okay, you would have, or let's say we compare a narrow line with a wide line. They're both L long, and this is, I don't know, W1, this is W2. L. So both of these would have the same fringe capacitance. But of course, this one would have higher parallel plate capacitance because that's area dependent. This is just length dependent. Any questions about that? So basically, this is what you'll end up with. You'll always get a table, and these are the sort of the capacitance you have to worry about. You draw your layers, and typically you're going to use the tool to get the actual values for simulations, but this you can use for planning, etc., to figure out what to route where. Okay. So just going back, the other thing to worry about is this gets really complicated. As I'm telling you guys this, these are just really simplifications, but you have the capacitance of a wire. If you have a plate on, if the wiring is indeed complicated, which it is, you have just a mess of wires. You have a rat's nest. When you look at the wiring of your chip, just the really complicated wires. And so you have wires on top, wires on bottom, wires on the side. And these are all affecting your fringing fields, affecting your capacitance, affecting on how much things talk to each other. So, all these are simplifications because every new wire you add, every new piece of metal you add to this picture is affecting the rest of your capacitances. It's affecting the overall electric field. But if you consider all that stuff, it's too complicated. So what people do is they just sort of keep adding capacitances as if they're individuals that aren't affecting each other. So, if you have adjacent lines, you drop in the capacitance for adjacent lines. If you have top and bottom lines on top of your layer, you add those. Let's see what else. Okay. I think the main thing I want to say about this, because I think most of this is pretty obvious, but that one of the things that people are trying to do, just like people went from aluminum to copper to reduce resistance, people are using something called sort of low K dielectrics. So the K stands for this dielectric constant that you multiply by the permittivity of free space for a material. For silicon dioxide is 3.9, but they use lower material with lower K values to reduce the capacitance. And this is an ongoing thing. I still see a lot of silicon dioxide, but there's just people are reaching at every little nook and cranny for finding a little bit of an advantage here and there. By the way, guys, I was trying not to, just the thought occurred to me. I was trying not to go off on a tangent, but I think it's interesting. So I'm sure you guys have heard of Moore's law, right? We talked about a little bit. Maybe you've heard it in other places, but I thought this would be kind of a good place to talk about it. But or rethink about it. So Moore's law was this concept that processes, chip or semiconductor processes, chip design processes, whatever you want to call it, were getting, you could put in twice as many transistors, or what was it, every 18 months, something like that. And you basically could count on the improvement of the process capabilities happening every 2 years to get your improvements in processing power. Now that started slowing down a few years ago, and there's a raging, like the big debate at the highest level in chip design is Moore's law dead, or does it still have life in it? And there's a lot of disagreement there. I think the majority think that Moore's law is dead or dying, but the diehards still claim that it's going to continue for many years because, if you look at any one thing, it's, might be running out of juice. And the examples in interconnect we're talking about today, well, the resistance, we go from aluminum to copper, you get a little bit of improvement there. Or, the dielectric, you use some other dielectric and you go from 3.9 to 3. None of these things by themselves get you to these factors of 2 improvement in performance every couple of years, but there are so many of these factors that the process technology people are working on. There may be thousands of these things that they're working on to make the transistors faster, to make them smaller, to make the interconnection smaller, lots of these factors. And they believe that given all of these factors that are, that can get traded off and improved, there's still lots of room in, an improvement in the performance of chips for coming generations. And this is the reason I popped it out, because I just sort of a topical discussion point. But also you can kind of see it. Nothing here when we're talking about these moves from, say, aluminum to copper. It was a huge, huge change in the industry. It caused a lot, cost a lot of money for the foundries. It caused a lot of complications in the design, the modeling. Same with the low K dielectric reliability issues. These were, we're using just a few sentences to describe them, but I kind of lived through these transitions, and there were big deals. But you have to have a lot of these things to happen to all add up to sort of significant changes. Anyway, so we'll see. You guys are young enough that you'll see if Moore's law is dead or not in a few years. So we'll see what happens. Okay, so sorry about that digression. Let's see. Okay, so let's do another example here. Again, you guys can take a peek if you want. This is right on the next page, but let's see. So it says, okay, so this is, we're trying to estimate, whoops. So that's not green, is not good. So we want to get the delay of a 10x inverter, and it's driving a 2x inverter at the end of a 1 millimeter wire. Okay, so this is a 1 millimeter wire. What else we want to say? So the capacitance is 0.2 femtofarads per millimeters. And a unit size inverter, the R is 10k ohm, and the C is 0.1 femtofarads. Okay, so that's a unit. Remember, a 10x is 10 times as wide as the unit 1, and a 2x is 2 times as wide. Let's see, what else do I want to say? Oh, and then let's say the resistance of this wire is, sorry, what is this thing saying? 0.2 femtofarads per. There's a bunch of stuff missing from this. Let me just make up some other stuff. So it's 0.2 femtofarads per micron. Okay, and the resistance is, let's say, 2 femtofarads per millimeter. Let's see. Let me just do this. Sorry, guys. Because this is like, I think my slide is hosed up. So I'm just going to say, just give you the total resistance of this line is 800 ohms. Okay. And then the total capacitance of this line is 200 femtofarads. So the question is, what is this modeled as? you guys give that a quick try. So the hint is you guys want to do you can do a single segment pi model of this, and then you have to look at the output resistance and the capacitance and the input capacitance of this. Okay, guys, any volunteers? No? Christian, how about you? Can you help me out?
I'm still trying to figure this out. I'm a little lost.
You're a little lost? Okay, we'll figure it out together.
Okay, okay.
Let's figure it out together.
You said to make a pi model of the wire, right? So I did
Yeah.
that. So it's
You already
800
did that?
ohms. Huh?
You said you did that?
Yeah. So it's just like 800 ohms across, right? And then you have the 200 femtofarads capacitance going downward to ground, right?
Yep. Yeah, that's the biggest. So it's 100 femtofarads on each side.
Okay. And
So you
then
got
that's all
that.
as far as I got.
Okay, cool. So let's look at this this inverter that's driving it. All right. It's what does that look like? Let's say you would, if you're doing this, remember that this sort of equivalent resist inverter, it's tried to make its pull up and pull down resistances the same. So you only need to like look at the pull down or the pull up resistance. So just let's think of the pull down resistance, right? If you just had
Right.
this N MOSFET pulling down, what would the resistance be?
It would be 1K, right?
Yes, it's 10 times as wide, so it's
10
basically
times.
got a 1 kilo ohm resistor.
Right.
And what would the capacitance be here?
Um, 0.01 femtofarads or no?
Yeah, that's for one sort of unit capacitor, right? Remember that an inverter has three of these, a unit inverter. Remember the parasitic was like 3, so it's 3 times
Oh.
0.1,
Mm-hmm.
and then it's 10 times wider, so it's really 3 times 0.1 times 10. So this total capacitance would be 3 femtofarads.
Oh, okay, yeah.
Did that make sense?
Yeah.
So I mean the cool thing, I mean one of the points that this problem is trying to say is look at, it's basically you can ignore it essentially when you have this long of a wire. The capacitance is only 3 femto and you already have 100 femto here. So it's only, it's a very small part of the total capacitance when the lines are long. Okay, so and now let's look at the 2x inverter on the here. So basically, because we're driving a gate, we only have to worry about the gate capacitance. We don't need to worry about the resistance because it's only the only thing you'll see in your delay is these two gates. So when you're driving this thing, you don't worry about the resistances, etc. So do you remember the gate capacitance of a 2x?
I'm looking for the chart right now. I don't know off the top of my head. For the gate, is it? Wait, is it for invert? Is it just one, or am I wrong here?
Well, so what happens is, let's look at it together. So for a gate, so a typical inverter, this was a 1x and this was a 2 times width, and the P was, sorry, N was 1 times width, P was 2 times width. And each one of these guys had 1C of capacitance. So it was 3C, or in this case, 3 times 0.1 femto. Okay, but it's a 2x inverter, so you multiply it by 2. So you end up with, what is that, 0.6?
Oh, okay, yeah, that makes sense.
0.6 femto.
We don't care about the resistance because it's the output, and we're only looking at the gate, right?
That's right. So when you're looking at the delay, you're only looking at sort of like up to here. So from here to here. So you don't really look at the resistance. There's basically, you want to see the delay getting to this gate.
Got it.
So again, you see that this stuff is pretty small compared to this 100 femto. So you can, you can add it up, but like, so really the resistance matters of the inverter driving this thing, and the capacitances don't really matter. But anyway, that's like the model of driving a line. Anybody have a question about that? Thanks, Christian.
Yep.
Any questions? Okay, that's that guy. Okay, and just, I think I'll stop here, but basically the idea is that as you draw, as you have these different interconnects, you can just treat them as like Elmore delay. Basically, you create pi models of the different interconnect, and you can use Elmore delay to, just like we did for the logical effort to figure out the delay. And then so we'll pick it up at crosstalk next lecture. Any questions? Okay. Take care, guys. See you on Thursday.
Thank you, Professor.
Thanks. Bye.